Assalamualaikum and selamat sejahtera. My name is Muhammad Amir bin Muhammad Nur. Its number is B1224104415. And we have Muhammad Nabil bin Tajuddin, B1224108484. And today we're going to present about the digital signal processing window filter, which is the filter that we are choose is a BERT and Kaiser window. So firstly, we have set for this topic. This study we focus on windowing filter that is used in digital signal processing. The BERT and Kaiser window are usually analyzed and going to be compared in FIR filter design. So we are going to use MATLAB to study the frequency response and also for real application. The result will show that the window is simple and also efficient at the same time. While for the Kaiser window, it will provide better spectral performance. Next, we going through the introduction and the purpose of windowing. For the introduction, we know that filters are usually used to allow desired frequency to pass and will block unwanted ones. FIR filters are commonly used because they are stable and have a linear phase. By windowing techniques are applied to improve filter performance. So different window will affect frequency response and spectral leakage in different ways. So for the purpose of windowing, ideal filters have infinite length and cannot be implemented directly. Truncating the filter will cause spectral leakage and also will cause ripples. Windowing will reduce these effects and will improve practical filter performance. So we going to the first filter that we choose is Kaiser window. By looking at the graph here, we see that the Kaiser window is a flexible windowing method that are used in FIR filter design. It can be defined by an adjustable beta parameter which will control the window shape. This flexibility will always allow better control of the frequency response of the filter. The Kaiser windows is usually widely used in applications that require higher spectral performance. Then we go into Kaiser window characteristic. We're going to know that the Kaiser window, when the beta parameter of the Kaiser windows control the trade-off between main loop wide and side loop attenuation. A higher beta value will reduce side lobe levels and spectral leakage, while a lower beta value will produce a narrower main lobe with a higher side lobes. This adjustability will allow precise tuning of filter performance. So for the Kaiser window application, the graph side show the audio noise reduction made by Kaiser window. It is an important application of the Kaiser window is applied in audio noise reduction. In audio systems, high frequency noise can reduce sound quality and listening comfort. A low pass FIR filter using the Kaiser window can reduce this noise, while keeping the main audio signals clear. The adjustable beta parameter will help balance noise suppression and signal clarity, which is making it suitable for music processing, speech enhancement, and lastly, hearing aid system or any other sound. Next, we're going through a second filter that we choose. Second window that we choose is a ballad window. The ballad window, we like the graph showing, which is a triangle here, is also known as the triangle window, which also is a simple window technique that used in FIR filter design. It has a rectangle shape like this graph show, where the window's values increase linearly from 0 at the edge to a maximum at the center. This way, gradually tapering helps reduce sudden signal discontinuities. As a result, you can see that a spectral leakage is lower compared to a rectangular window. Move on to a Bartlett window characteristic. How do we know Bartlett window? The Bartlett window has a wider main loop, which result in moderate frequency resolution. It will provide moderate side loop attenuation, means that some unwanted frequency still can present, but the window values are 0 at the edge, which smooth the signal in the time domain. Due to its fit shape, the trade-off between main loop wide and side loop suppression cannot be adjusted. So for the Bartlett window application, for example, we can apply it to a signal smoothing and noise reduction, as we can see in the graph. So the Bartlett window is a simple computation. The Bartlett window is commonly used for signal smoothing and low pass filtering, where simple computation is always required. Because the Bartlett windows can reduce high frequency noise in audio signals while keeping the overall signal shape. Its triangular shape will provide moderate side loop attenuation, which helps reduce spectral leakage. This makes the Bartlett window suitable for basic noise reduction, signal averaging, and also for sensor data processing. That's all for Bartlett and Kaiser. We move on to the
Assalamualaikum everyone, my name is Muhammad Nabil bin Tajuddin. My matrix number is B12241048. So I will present about filter design. So our filter design is the Bartlett window has a simple triangular shape that reduces sudden changes in a signal but offers limited frequency resolution and side lobe suppression, making it suitable for basic smoothing and simple filtering. The Kaiser window is a smoother and adjustable using the beta parameter, allowing better control of side lobe and frequency performance, so it is preferred for more accurate and advanced signal processing applications. So for our unit impulse response, here is our code parameters. So n is equal to 81. This is the length of the impulse response. So the outcome result will be odd. So FC equal to 0.1, which is a normalized cutoff frequency. Then n equal to 0, n minus 1, and p equal to n minus 1 divided by 2. This is for center index. So next, for the truncated sine function, H equal to sine 2 pi fc P divide by pi multiply by P. So H n minus 1 divide by 2 plus 1 equal to 2 pi 2 multiply by fc. So this function is to handle division by 0. So for plot unit impulse response, figure stem and HR line width 1.5. Title for our output unit impulse response of truncated sine function, and x label is n, y label is amplitude, and grid on. So here is our result. The result for unit impulse response of truncated sine function. So here is for the frequency response of the filter. We set the n equal to 81, fc equal to 0.1. So for frequency response, we just need to change to the h and w equal to frequency z, which is h1 and 1024. So for plot frequency response magnitude, so we need to set figure, plot w divide by pi abs h, then b for blue, and line width is 1.5. Then we grid on. So our axis x label is normalized frequency times pi red sample, and y label is magnitude. So our output title will be a frequency response of the truncated sine filter. So here is our output. The blue line is the plot of frequency response. So next is our frequency response of the filter. So H value frequency Z, H1 and 1024 is a frequency resonance of sine C. Then H value equal to frequency Z, H1 1024 is a frequency response of window sine. So we plot W by 20 multiplied by log 10 ABSH with the red color, and line width is 1.5. It means the sine frequency response in dB. So our title is magnitude in dB. Then our x-axis label is a normalized frequency times pi red sample. Y label is magnitude dB. And then there is a grid on. So our legend is sine function and window sine function. So here is our Kaiser windowing filter. So this is a code to have the output of Kaiser window, beta equal to 6. So we can see a stem and omega and W Kaiser with red line, which is R, line width 1.2. Title is Kaiser window beta 6, and X label is N, meanwhile Y label is amplitude, and there is a grid on. So next is a Kaiser window filter. We have a subplot J1 and 3. So stem and H Kaiser are line width, and title is unit impulse response for Kaiser window, which is beta equal to 6. X label is N, and Y label is amplitude. So same with the grid on. So here is for the magnitude response in dB. So we need to set n equal to 81, beta is 6, n is negative n minus 1 divided by 2, then n minus 1 divided by 2. So here is for the filter length, Kaiser window beta, and sample index. So we put our ideal sine low pass, WC equal to 0.2 multiplied by pi. Here is for the cut off frequency, and H sine is sine WC multiplied by n, then divide by n. H sine n plus 1 divided by 2 equal to WC divided by pi. This is for handle n minus 0. So for Kaiser window, W Kaiser equal to Kaiser and beta. For H Kaiser equal to H sine multiply by W Kaiser. So our frequency response is H sine equal to frequency Z, H sine 1 and 1024. So H Kaiser, which is frequency Z, H Kaiser 1 and 1024. So for plot magnitude response, we put a figure and plot omega pi 20 log 10 APSH sine R, which is for the red line, and line width 1.5. Then hold on. Then we plot the W by 20 log 10 APSH Kaiser, which is B for the blue line, and line width is 1.5. So we put our title magnitude response in dB, X label normalized frequency times pi red sample. Then Y label is magnitude, so legend is sine function, which is for Kaiser window sine. Then our grade on, then we put the whole off. So here is our result. So here for Kaiser windowing filter, so plot which is W divide by pi 20 log 10 APSH Kaiser, which is a blue line, so we put a B. Then line width is 1.5. Then H Kaiser W equal to frequency Z, H Kaiser 1024. Then H ideal to infinity is a frequency Z, H ideal 1 and 1024. So our figure, we plot W by 20 log 10 APS H Kaiser, the blue line, so B. Then we put line width 1.5 and hold on. So next is we plot W by 20 log 10 APS H ideal and the red for line width. So here is for the transcript for the ideal. Then we put the X label normalized frequency times pi red sample, and Y label is magnitude in dB. So our title is magnitude response comparison. Then our legend, we put Kaiser window and truncated window. So the result will be like that. So next is our Bartlett windowing filter. So to have this output, we need to stamp and W Bartlett, B for blue line, then line width 1.2. We put our title is Bartlett window, then X label N, then Y label is amplitude, so we put our grade on. Then here is our result for Bartlett that have a triangular shape. So for Bartlett windowing filter, to have this unique sample response of the sine function for Bartlett, so we need to first stamp and H ideal red line, then line width the 1.5, then hold on. Next is stamp and H Bartlett, B line width 1.0, title unit sample response of the sine function Bartlett. Then we put the legend for truncated sine, then window sine, then we put a green on to have this output. So we need to have the code. So next for the Bartlett windowing filter is a magnitude in dB. So here our magnitude in dB is we need to set a frequency response of sine, then frequency response of window sine. So Hz and W2Z, frequency Z. So H T2 or W2 and T2 equal to frequency Z T2. So for plotting, we need to plot W2Z divide by pi 20 log 10 ABS HZ with the red line, then line width is 1.5. This is for sine frequency response in dB. So we put the whole on. Then next we plot W2 T2 divide by pi, then 20 log 10 ABS H T2 with the blue line, so B. Then our line width is 1.5. This is a window sine frequency response in dB. So we put our title is a magnitude in dB. Then X label is normalized frequency times pi red sample. Y label is magnitude. Then we put grade on, then put a legend to sign function and window sign function. Then we put a hold on. So next, for the frequency response of the filter magnitude, we put as Z, W to Z for the frequency response of sine. Then H T2, W2 and T2, frequency T2. Then plot W2 and Z, divide by pi. We have ABS H and Z with the R for red line and line width 1.5. Then for window sine frequency response, we put blue with line width 1.5. So we put our title as frequency response of the filter magnitude. Then X label is normalized frequency times pi red sample, and Y label is magnitude in dB. So we put a grid on and legend with the sign function and window sign function. So here is our for filter design. This is a picture for time domain before filtering, and here is a time domain after filtering. So you can see the scene is getting smoother. And here for the frequency domain, we have before filtering is have a lot of noise. So when we put after filtering with the frequency domain, the signal getting smoother and better. So for real life application, Kaiser window is suitable for high performance applications such as 5G, OFDM, radar and medical imaging. So Bartlett window is suitable for low power and basic application such as speech processing and walkie-talkie. This is provide decent noise smoothing but lower frequency resolution than Kaiser. Hello everyone, so here I'm going to show you our simulation. So as you can see here in our lab report, we have our code for the all command that we need to use to have our result. So here I'm going to attach the code from our report to our command window to have our first result. So here you can see that we copying the code from our report to our command window. So here is our result, and the top is highlighted. It have a triangular shape, and at the bottom is a Kaiser which have a bell shape with beta equal to 6. So here we copying the magnitude response here at the command window. So when we pasting our result to command window, here is our result. You can see the magnitude response comparison. For Kaiser, it at the top which is at 60 dB. Meanwhile the Bartlett is start at the 0, and then at the 0.2 it's plummet to the down at 0.5 and starting to get stable at the near to the 1. So here we're looking at another code. Here is to find the magnitude response between Kaiser and Bartlett. So as you can see here, the main lobe with comparison, you can see the Kaiser at the red and blue is a Bartlett. You can see blue at the bottom, meanwhile the red at the starting to 1000 and plummet down until the 0.3 at the x-axis. So next we are copying the another code and paste at the command window, and here is a effect of Kaiser beta on frequency response. Here we have 3 beta which is beta equal to 2, beta equal to 6, and beta equal to 10. So each beta have their own frequency. So next one, we will use other code that we have provide here. And as you can see, here is a time domain before filtering, and this is after filtering. The signal becomes smoother, and at the frequency domain before filtering, we have see there's a lot of noise, but when the frequency domain after filtering, it's getting smoother and better. So that's all from me. Thank you.
Discussion, the Bartlett windows offer simplicity and low computational costs. The Kaiser window while the Kaiser window offers flexibility and a better frequency control. These two windows are good, but the choice of window will depend on how the application requirement. Performance must be balanced with complexity. And finally, we have conclusion. This study successfully compared the Bartlett and Kaiser window filter. Like we said before, the Bartlett window is suitable for simple and low-cost application, and the Kaiser windows provide better spectral performance and flexibility. The result highlight the importance of choosing the correct window for specific signal processing tasks. That's all from me and Nabil. Thank you so much. Assalamualaikum.